Oh, it's not here. All right. So I did a little review sheet here. So these are all the reactions that you need for this chapter. I'm gonna post it somewhere here. I'm gonna give me a second to share my desktop. All right. Where is it? All right. I'll share it here. See if it lets me. Damn, it's not letting me. Okay. I was trying to share this with you guys. It has all the reactions of the chapter that you need, but it's not working in the whiteboard. Professor. Don't call me professor. I'm not a professor. All right. All right. So I guess we'll do it by hand. So, all right. Why is it so small? Okay. Oh, forget that. Whiteboard. Just give me a second to settle in. All right. Erase this. All right, there we go. So the first reaction I'm gonna go over is this one right here. Before we do the problems, I'm gonna give you guys like a little cheat sheet of the reactions you need right here. Okay. It's called the Williamson ether synthesis. All right. So it looks like this. It's an R group. It's like a hydrocarbon group. Okay. This reagent is like the best thing, the best example I could give. It's the one you need. Okay. R over X. All right, guys. So that's Williamson ether synthesis. So what happened here was this guy right here, the hydrogen, has a negative charge, right? And then it's gonna take this guy right here, that hydrogen, and then
How do I connect my AirPods to my thing? How do I connect my AirPods to this?
if you're asking
Yes.
me, I don't know. Okay. Okay, so then that hydrogen is gonna act like a nucleophile. It's gonna attack this alcohol right here. It's gonna be O minus, right? And then this RX right here, the second step clearly, what's gonna happen is an SN2 attack. From Orgo 1, you should know what that is. What happens? That's gonna attack this. And this goes here. And that's how you get this. It's like a little mechanism of the reaction. You don't gotta know this, but some people learn like this. So, all right. But what I want you guys to write down is just this reaction. That's the reaction you need for that one. Okay. Next reaction we need right here. It's the same reaction, but intramolecular. I'll show you what that means in a second. Okay. Oh, by the way, let me undo this actually. Hold up. It's important too. I'm gonna give you guys like some rules that this follows. So let's put the rules here. All right.
Yeah.
Steric should be considered.
Hey, give me toxic love.
All right. What does that mean? Right? This means that if you have like a bulky molecule, for example, like butyl, something like that. Yo, can you mute your mic, bro? Oh, please. I forgot the mic on. What is that? All right. Hold up. Maybe mute this guy. There we go. Well, I turned my camera on, so by accident. All right, let's keep going. The steric effect should be considered. What does that mean? If you have like a bulky molecule, like for example, like a terbutyl, it could complicate things because this only works with a primary halide. Only works with primary halides and this XCH3. That's like not even a primary. That's just like a methyl with the halide. That's it. That's the rule. It only works with that. So if you have like a secondary halide or like a tertiary, it's not gonna happen because remember SN2 does not happen with those. So don't forget that, guys. All right. Only works with these guys. So I think that there was a student like Uzman. He said that. Yeah, like you were confused. Well, the confusion's gone. It only works for primary halides and that. It's more efficient. Now we're done with this. Now we're doing intramolecular. All right, so I'm gonna give you another example of it, how it looks. All right. Okay, see, terbutyl right here. All right. And a little note about this. Must have a compound with an OH and a halogen. Note 1, note 2, the O minus, which is the nucleophile. Any questions? Yeah, it kind of looks whack. I'll do it again. Let's see how. Let's put it in a different color so it doesn't confuse you guys, I guess. Wait. All right. Let's see how. Yeah, that's terbutyl. Yeah, or a bulky. Hold on, I was typing though. No. I'll put it here. Oh yeah, that's the note you needed. Doesn't really matter. Okay, so what happens here, right? There's two options. because this nucleophile could do like an SN2, right? Let's say, right, like I'm saying, this attacks here, and then this goes away. But like I said, remember that this type of reaction is an SN2, so a tertiary doesn't work, right? It's too bulky as well. That's why this doesn't happen. What's going to happen instead? Oh, damn. Is this. I'm going to attack this right here, take that hydrogen away, right? And then it's going to look like this. I'm doing the mechanisms because in this class, you got to know the mechanisms. He tests a lot on that, right? So what happens there now, right? That's step one. That's step one. Step two, well, it's kind of intuitive, intramolecular. So that means like that the molecule is going to attack itself. How? I'm going to attack this, like an SN2 attack there. And that goes away. And then obviously like it comes together and then you get this. That's all that happened. It looks kind of weird, but nothing really happened. Just it attacked itself. It's not that complicated, this reaction. It's just like an SN2. But you need like a bulky base like that because it doesn't do an SN2 attack right away. That's all that really matters for that one. Yeah, it's terbutyl. Okay. All right, those are the two first reactions, the Williamson. It's a pretty easy reaction. Okay. The next one I want to talk about is something that's kind of similar to something you learned in Orgo 1. This one right here. Looks like this.
We were skipping that.
You skipping this one right here?
Yeah.
You sure?
Yeah, I even went to office hours and said he was skipping it.
I
But
don't
you
know.
can check with him. You can do it and then check.
I mean, no, if he's skipping it, he's skipping it. But I mean, he tested this. All right, doesn't matter. All right, no problem. All right. A little recap from last semester right here. We're going to use this again. This right here. MCPBA, right? This reaction. So from an alkene, you're making an epoxide. How? MCPBA. The mechanism is very complicated. You don't got to know that. But there's some rules about it, right? So it's gonna look like this. That's a wedge. Okay. A little rule that maybe could help you out. It's very specific. Like for example, like if the molecule is already cis, once the reaction is completed, it stays cis. That's all. What does that mean? I'll show you in a second. For example, we got this. We got an R right here. We got an R right here. Right? I got a hydrogen right here. I got a hydrogen right here. All right. All right. Then we got this. It's like another like type of MCPBA. It's another acid, but doesn't really matter. The point is this. It's gonna look like this. Like I said, right? See how the R's, remember like the E and Z stuff that you learned in Orgo 1? Well, that comes to play here. So these two R groups stay the same. These right here. See how like they're cis, same side. So make sure that when you do draw that they stay the same. All right. All right, that's all I wanted to show. And the name of this is hold on. It's not a Williamson, this is, it's not this, it's this. So just in case you guys need to know what, it's pretty intuitive, but it's called preparing epoxides using alkenes and peroxy acids. There's two types, like I said. This one, last one right here, and this one. Oh, what did I do? Oh, okay. All right, yeah, MCPBA, and then this. Just use MCPBA. It's easier to memorize. Okay. We have done 3, we skipped 1 because according to one of you guys, you're not doing that. Okay. There's another way to prepare peroxides, right? And put it right now. Allohydrins and alkenes. Hopefully you guys are writing this down because it's my notes that I used. And it helped me out. OD. If not, it's okay too. Okay. The first reaction I want to go over is this one right here. And by the way, this chapter is like, it's not like emphasized like as much as the other ones, but like whoever's like wants an A+ here, then yeah, it's important. But like, to be honest, like it's not like the end of the world if you don't get this chapter because it's not that enforced in the exam. Has he posted the exams yet? Oh, so well, today's your lucky day because I guess we're gonna do some exam problems afterwards. I can't show you it like the whole exam if he hasn't showed you, but we'll do some problems. Okay. So some of the rules about this right here, this reaction, an anti-mark. All right. But that's not important. Okay. Another reaction that falls in the same category. Okay. Oh, got it. I see what I have to do. So that's the first step, right? And let's say like, it's already like this, right? And he gives you a BR. Basically is that what I just did, but he adds this right here, NaOH, right? What's gonna happen is this. Oh, it's horrible. It's gonna make the epoxide. That's what we wanted. So to put this all together, I did it step by step because it's important to know what's happening. What happens is this, BR2, H2O. And then second step is what I just did, the NaOH. Yeah, then you just get an epoxide. These are different ways to make epoxides. So I showed you two right now. So you have two options, just in case there's a synthesis with that. Most likely not, but maybe. I don't want no surprises for you guys. All right. Can I erase this? What's the benefit of using? So there's no benefit really. It's just like a different option. Yeah, it's good to know like different ways to do it. Because he might ask you like just this part, for example, like he might be like, okay, wait, what? Like what happens here? Or like what happens here, you know? Okay. All right. So we did 1, 2, 3, 4. Okay, now what he really asks about is this though. Okay, so let me see if that could. I want to write this down if it's here. Actually, it might be confusing for you guys. So, can you guys see this? I can't see the chat, so someone just say yes or no.
It just looks blank to me. I just have a white screen.
Oh yeah, I have the whiteboard on. Okay. Okay. Actually, never mind. I just stay with the whiteboard, just to not draw confusions. Okay. The next thing I want to talk about is opening an epoxide, right? There's two different ways. You could do it with a nucleophile and like a Schwann base, or you could do it with like an acid. So let's do first opening it with a base. Ring opening, epoxides with strong nucleophiles. So basically, guys, what I'm giving you guys here by the end of this notes is all you need for the chapter. Like realistically, you'll be fine. So let's keep going. Okay, so that's the main note and little side notes. Like just showing you what happens. Nucleophile attacks. That subside. And if the area that is attacked has a chiral center, you know, just inversion happens, like a SN2. Inversion is like if you have a dash, you attack it, it becomes a wedge. That's it. That's pretty much what I have the notes with. Okay, there we go. So there's a lot of them, right? That could happen. A lot of reagents. It's R, ONA. Wait, no, let's write it better. R, O, Na, over H2O. Okay, and then it just becomes like this. Once it's open, it's in your book too, what I'm writing down right now, but I don't want to confuse you guys. Another one is NaCN over H2O, cyanide. What's another one? It's good. R, Mg, Br. You definitely know this. It's Grignard. And they're all like nucleophiles. They all have the same. You don't gotta memorize everything. Just make sure like you know it's a nucleophile. How you know? Well, CN has a negative sign. MGBR, you know the R group is negative, right? ONA, NA is spectator positive, R is positive, so this is negative, right? Just know like what happens, right? Don't memorize every single reagent. If they're equal in how they react, memorize one, but the process, that's it. There's no point in memorizing everything. You're gonna see like later on, there's like 40 reagents, the same thing they do. All right, but that's not until exam 3. All right, that's CN. See, it's the same thing they do. OH. Let's see if I'm missing one. Might be. Oh yeah, one more. This one's man common as well. It's like La, I think. Oh no, similar to La. And it has the same thing. I'm not gonna write down the what it does because it's evident. Okay. So these are the most common ones that he could ask. I don't see no more. For these are common strong nucleophiles that open epoxides and they attack like the more subside. So for example, we have an epoxide here as an O, right? And you'd be like, where does it attack? There's an attack right here. Okay. We're gonna do problems, so don't worry about it. Can I erase this? Just anyone, say yes or no.
Yes, yes, yes.
Oh, what's up, Abdul? I saw you were here. All right. All right. So what's next? Okay, yeah. So now we looked at it from a strong nucleophile point of view, right? But there's also acid catalyzed. It's the only tricky part maybe because it's opposite. But like the reaction itself is just this, right? It's gonna be an O. And it's H over X, where X could equal, you know, an halogen, usually like Cl, Br, and I. F, why not F? Well, it's not really good with reactions. It's very unstable. The only like difference here is that the epoxide opening, right, happens on the more how do you say it? The side that has more substituents, okay? But I'm gonna say subs for short. It's pretty straightforward. So basically it's opposites, okay? And just remember, like, of course, like a mechanism, right? It's different, the mechanism. For example, like here, what happens first is you need to get a positive sign, right? Because it's acid catalyzed. Remember, in mechanism, you cannot have a negative whatsoever if there's an acid, okay? Or if it's like the whole reaction is about acid, you cannot have negatives, never. So first you have like a positive, and then like you have like the attack, just a little key point. But we'll do problems, well, it will make sense. And don't worry about like thiols and like sulfides. That part of the chapter, I have it in my notes, but then he said he was not going to test it on it. So I'm pretty sure he's not going to do it neither with you guys. Does anyone know? Because obviously,
He skipped,
what? I couldn't
Yeah,
hear
he's
you.
not gonna do the
he
dial.
skipped it. He didn't do it.
All right, good, good. Yeah, so don't worry about that. So that's pretty much it, like for the chapter, right? Like notes wise, of course. We're gonna do like the questions right now, but that's all I used in the exam for that part, and I did okay. So I don't need much for that. Let's keep going. All right, I'm gonna share my desktop. See where it's. So we'll do the first problem. Okay. It's not working. Let's see here. Let me just erase this. Give me a second. The website's good to use. Is it not working? All right, hold on, plan B. All right, I'm gonna try to fix this. Give me a second because I want to do the problem with you guys. All right. Okay. All right, so that's the first assigned problem that he gave you guys, right? So let's do it. So it says starting from a cyclohexene, try to make A, B, and C. All right. Let's do this. So forget about these for now. All right, we have a cyclohexene. Read the instructions. You can use any reagents of your choice. You know this. Think of it like a little synthesis problem. So one way, right? Well, you guys had to skip that. I don't know why he would say to skip it, but the easiest way to use would be that. But another way to use this, right, is how do you make an alcohol, right? That's Orgo I stuff. Any ideas before I say it? Well, if you're typing in the chat, I can't hear you. I can't see the chat. So I'll just say it. The easiest way that comes to mind is if you use dilute H2SO4, right? When you do that, what happens? We'll just erase this. You get an 8, you get an OH. It's basically like an SN1 attack, but I'm not doing all that right now, but it's an SN1. Okay, then what happens, right? We need to make this part. How? Well, we learned remember the William synthesis? What did I say about this reagent, right? NaH, right? And then we could use, how many carbons do we have here? Think of it. We have one, hold on. We have 1, 2 carbons. So 2 carbons, it's an ethyl, right? That shouldn't be surprising. So ethyl, someone asked, I can't read the chat right now. I can't see it. So if you have a question, just speak up. So here you see the hydride attacks the alcohol, then the alcohol has a negative. I mean, the O has a negative. It's gonna attack this alcohol halide, right? And then what happens? Looks just like A. Any questions? That's the first problem we just did. That's your first assigned problem, basically, part of it.
Can you just put like an arrow saying like how the O attacks the ethyl?
Yeah, I got you. No problem.
Thanks.
So what happens, right? Let's do the mechanism. Yeah, it's important. So NaH, right? Na, and then there's a hydrogen right here. This hydrogen is a negative, right? It's hydride, basically. It's like a nucleophile, strong one. So it's gonna attack. Let's use the arrow, different color, so that doesn't confuse no one. We're gonna attack this right here. This is gonna be like this now. So gonna be O minus right here. We're gonna be left with ethyl. Actually, let me draw it out. So you see what happens. You got ethyl. You got I right here, right? I or Br, whatever. So then what happens, right? This alcohol, I mean, this oxygen right here is gonna do an SN2 attack. It's gonna do that. It's gonna attack that carbon. It's gonna release that iodine. And then you get your final answer. Did that make sense? Whoever asked. All right. All right, cool. So that's the first problem. I'm not gonna do B and C because
Wait. Where did you get iodine from?
remember here.
Yeah.
Let's go back before I did this. I mean, remember when I was giving you the notes about the Williamson ether synthesis?
Oh. I
Remember
get
it's
it.
Rx, and the X is a halogen, right? What are the
Yeah.
what are the halogens again, right? I, Br,
Mhm.
and Cl, right?
Yes, sir. I'm clear.
Yeah, so you could use any of them. I just prefer
Oh,
to
so it
use
could be Br2.
yeah, yeah. You
All
could,
right, thank you.
no problem. Not F though. It's too unstable. He likes to test your chemistry, so not F is not good. B and C, same concept. I don't want to waste your time on doing the same problem again. Okay. So B and C, practice for you guys. You could do it on your own. Okay. Okay, now it's the Williamson reaction, right? The one we did before. It's the same thing, but just intramolecular. I'm thinking to see which question I want to do to test the better knowledge. Okay. We're not gonna do 32 because 32, y'all could do 32, okay? Because 32 is just the same thing, just that it's intramolecular, okay? So it's the same thing we just did. And he's gonna test you maybe one question about this, so don't worry about that. Something he could ask you in the exam is similar to this right here, like 33. It's more like intellectual, like thinking. For example, like what is it asking, right? It's saying that methyl magnesium bromide, right? To react with this, it said it's very fast, right? You don't see the methyls right here. CH3. And then it says for this one right here, octane, slow, right? These questions for real, like something he might ask because he takes problems from here. Sorry, problems from here and just like kind of rewords them. So it's important to do these problems like he does. The problem sets problems. All right. And then it says that with this over here, it does not react at all. No reaction. That's what it's saying in those words. So we need to figure out why. So let's figure out why, right? Give you like a second to think about it before I go over it. Okay, so whoever was in Sonimus class, you saw something similar to this, right? Like you guys probably should know this by now. Like about ring strain. Does that ring a bell? Remember this term, ring strain? All right. Like basically like the closer you are to a cyclohexane, it's like optimal, right? Like it's stable. Oh, it's ugly cyclohexane, but nevertheless, it's just another one. Right? That's like optimal stability, stable. The one's like the least stable is this, right? The triangle, the one we have there, least stable. So yeah, I'm gonna repeat it once again.
Can you scroll down?
Yeah, I could. this question is going to be important. So if that's what you meant here.
No, it's just some of your writing is like off the screen.
Oh, you guys can't see the writing?
Yeah, like the bottom.
I don't know how to fix
I
that.
could see it. Maybe you have to just maximize your screen.
Yeah, that's what I'm saying. Joshua, that's good that you're thinking like that. That's what I wanted, you know? I wanted someone to think and say that. Yeah. So like I said, the reaction is super quick with ethylene oxide. Why? Because like it's not stable there. It wants to get out of there, right? So therefore, this reaction is gonna go quick. So your explanation, what do you say? It's because it's least stable. Therefore, the reaction wants to go forward. The octane says that it's slower, but it still goes through. Why? Because that's not really that stable either, you know? That cyclo, what, it's not that stable still. It's more stable than the ethylene oxide, but it still wants to go with the reaction at a slower pace, but still. And then the last one, right? THF. It doesn't react because think about it, it has like 6 sides here. If you think about it, with the O included. It's like kind of very stable. So like it doesn't want to react. It doesn't want to break its shape for the reaction to go forward. There's no benefit in energy. It has to do with energy. You know how he goes over that? I don't want to complicate you guys because I hated that too, but for real, like just you got to know these shapes. You have to. That's it. Hopefully it made sense. Cyclohexane, stable. 3 sides, not stable. This could be an exam question, so possibly. So put that here. Yeah, someone raised their hand. Go ahead.
So just for the test, we only have to put that the reaction will have a slow, fast, or no reaction.
Yeah, no, it's asking, right? No, it tells you that already. So it's asking like why.
Right. So you would have to put because of the ring strain. Like you wouldn't have
Yeah.
to draw that whole energy thing.
No, you don't have to do the energy thing. You could just say what I said, like due to its low stability,
Okay.
it wants to go forward with the reaction because the energy is favorable. If you like break a cyclohexane, you're gonna break its stability. So there's no reason to go forward with the reaction.
Right. Okay. Thanks.
No problem. But it has to do with ring strain, yeah. Just to go back again and recap. That's the main like term he wants, or like this problem wants. Okay. Hopefully that made sense, but that's the answer. All right. Let's see what another problem I want to do with you guys. All right, let's do 37. It's a lot of A through D. Okay. All right. Oh, no, you can't see that though. All right, we're gonna do A first. Can you guys see A?
Yes.
All right. So let's do number 1 first, all right? Let's do A, but number 1 of A. Forget about this for now. Okay. Just number 1, I'm asking, right? What's gonna happen? What is RCO3H?
MCBPA.
Well, it's like similar to MCPA. Yeah, it's a peroxyacid. Yeah, it's similar to it. So what happens, right? From an alkene, and you use that. We went over this, right? In the notes. Use the notes, guys. what happens? You get this.
It's gonna make an epoxide.
Exactly. Yeah. That's step one. For number 1, 2. It's a little messy, but yeah. All right, let's do number 2. Let me just do it again. It's a triangle. It's just like weird shape. I'm just following how it looks there.
Wait, so it doesn't matter where the oxygen goes on the triangle?
What you mean?
Like the oxygen right now is on the bottom right corner. Why can't it be on the top?
What oxygen are we talking? Like here?
Yeah.
There's 2 oxygens there. I mean, there's 2 hydrogens there. Oh, you're talking about the oxygen, right? Oh, no, I mean, it could be in the top, but it's better like that because you think about it, if it's in the top with that, right? These 2 on the top, they're gonna kind of collide, you know? You don't want to have too many steric hindrance. You want them like kind of far apart from each other. You know what I mean? Like you don't want them to be that close because then you can't do more reactions like that because it's gonna be packed. But it's not like a crazy thing. Don't think it's a big deal. Like, okay, if you have it right, you have it right. But you want it like that, like more, but it's not that big of a deal. All right. All right. So what's next, right? It says a methyl MGBR. What is that? That's Grignard, right? So you know that Grignard, that's together then. 2 and 3 are together because Grignard, it's MeMGBR, always followed up by water or H3O plus. MGBR. I hate writing this. Need an iPad. All right. How does that work, right? So, like I went over this already. I have it in your notes. What side is it gonna attack? Let's test that. Don't say it right now. I'm gonna put it in colors. Purple. You went over this, right? I give you my notes, so let's try to use them. Purple or green? Where is the Grignard reagent gonna attack?
Green.
Yes. Good. That's it. Good. So finally it's gonna look like this. How does that look, guys? Make sense to you guys? Could be tricky. First time looking at this. That's the final answer. Yeah, it makes more sense. Yeah, it's always more practical to do it. Questions, it makes sense. Just so you guys know what happened, right? This method right here, this one was right here, is this guy. That's the methyl, okay? Because remember, this bond breaks, right? Remember this. This bond is gone. All right, that's A. A is done. Let's see. Let's do B. I mean, no, we can't do B, right? Because someone said that he's not doing it. All right, let's do D. Here, Abdul, you see how they use CL? It doesn't matter. So just keep that in mind. We're gonna do D because C is like kind of covered. Let's do D. Wait, is there a positive charge on the OH? For which one, BB? What are we talking about? A or D?
For the product of the previous reaction that you just did.
Is there positive charge? No, remember, a Grignard, right? It's a strong nucleophile. So that means it has a negative charge. Every time you have a negative charge, there can't be a positive charge anywhere. Okay? Because that doesn't make sense. And when there's a positive charge, it's the other way around. You cannot have a negative. So keep that in mind. If you have a positive charge and there's no acids, something's wrong. All right, so D. Oh, someone's trying to get in. Oops. All right. Let's get this. NaETCl. Okay. What's gonna happen? So Na, they forgot to add the H. That's all. Don't get scared. That's all. Na is spectator. Doesn't do nothing. That's an H. What's gonna happen? The O. It's gonna look like that. Why? Because it lost that and then it attacked this. We did like 3 pounds of that. It's the same problem as the first one we did. That was not that bad. Okay, I don't want to confuse you guys with C, E, and F because I don't think he's gonna ask those questions. All right, let's see what other problems we could do. One of some hard problems. All right, you know what? Let's do some exam problems. All right, guys. First exam problem. Okay. So it says when treated with NaOH. Okay. Give me a second. I want to make sure of something real quick. See if he lets you guys. Pretty sure he lets me do this. Oh yeah. So it says when treated with an NaOH, one of the following compounds will form an epoxide fast. And it says, find the one that does and explain why it's very reactive, right? So do you guys want to try it? It's an exam problem, right? You guys want to try it and then I go over it? Or you just want me to go over it? It's up to you guys. I can give you like maybe like 5 minutes, 3 minutes to do it.
Let's try it, but can you make it a little bigger? It's kind of hard to see for me.
Okay, so try it out, then I'll give you guys 3 minutes then. All right. Is it better?
Yeah.
Oh wait, no, making it bigger isn't a worse. Hold on. You know, there. That's the most I could do because try it out. Give you guys like 2 minutes, 3 minutes. This came up like 2 times or 3 times in the exams. So it's an important question. So just if you get it now, you're in good shape. All right, it's already 103. Okay, never mind. It's already 103. I want to do some more problems because it's the only day I'm doing chapter 13. So just remember that. All right. So when it comes to these problems, right? When it comes about like stability or reactivity, and you have a cyclohexane, what you always do is a chair conformation because that's like the actual shape. So yeah, you have to go back to these guys. You guys remember these. So remember one, remember these. Okay. So you always do this again when it's asking about reactivity or stability. Said it 2 times already. And then you can start them anywhere, but I like starting them from here. Would be the answer because it's coming out the way. Oh, well, okay. I'll answer your question once I explain to everyone. So give me a second, baby. I think you're in the right track. Let's put it that way. All right. So OH, right? It's gonna be here. Hopefully, this is not new for you guys. It shouldn't be. BR is here. T butyl. All right. So I drew like, it's like the biggest hint, right? That I drew right here. Now, in the chat, whoever wants to pick A or B as the right answer. Yeah. It's A. It's A. Why? Because, yeah. That and because it's easier to do the S into attack. Like you could attack it. You could attack it. It's easier. Here, like, it looks uncomfortable. Basically, what I wanted to say basically was that, hold on, let me erase this because you want them to be in the axial position. This back attack. Stability could be like a small answer, but like the real answer is this. You want them to be axial because the SM2 attack is much easier to do. Does that make sense? It's 8 points. It's an important question. All right. I'm gonna clear this. Oh, that's exam question 1. Exam question 2. See, it's the Williams synthesis right here. Not that hard. So these are typically 3 points, right? The 3-point question right here. He'll give you like 10 of them, maybe, or like 9 reactions. I always do these in exams. Like I don't do 1, 2, 3, like all together in one. I'll do this. I'll go like, I'll do this, and then I'll show that I'm doing 1 first, right? So I get the extra points, but that's me. So I'm gonna explain it like that. What's happening here? The hydride attacks here. This goes here. Let me get O minus, right? Step 1 done. And just name it 2. But in this case, I won't do that because I teach. Okay. Okay, it's a good one. What side are we attacking? To make it a little more like, I'll give you all the answers. Purple or red? Where am I attacking? Red. Yeah. All right, 21% answer. All right, yeah, red is right. Oh. Wait a second. This chat thingy is on my way. There we go. I forgot I drew the O. And the last step, right? Hopefully that makes sense. What happened there? Because I didn't draw the mechanism, but okay. H3O plus, right? So what happens is this negative picks up an H. If someone got this right, that's good. You got 3 points in the exam. That's the answer. Did anyone get that? All right,
I have a question.
go ahead.
For like the 2 methyl groups, why isn't it closer to the top oxygen?
What do you mean?
Oh, I meant like, why isn't the 2 methyls closer to the bottom oxygen, not the top? Actually, I think I might be confusing myself. Never mind.
You sure? Let me undo this. Okay.
Yeah, so like, does it matter where you put the 2 methyls since there's like 2 places that you can put it?
No, as long as it's right, it doesn't matter.
So essentially in the second step from where you had blue and then you turned to the red color, that epoxide opened up.
Yeah. It opened up,
Oh.
right? Yeah, it's a little confusing, but you'll get there. That's the point of it, right? Like, we want to open them up. All right, that's another exam question. I don't know, this was a little more challenging. I don't know if I want to do this right now, but let me see. Let me see my classes. I have my last exam from last semester. It's up to you guys. I have a mechanism problem here. It's a little challenging, but we could do this, or we could just continue to do reactions. Where's the exact question too? I don't know if I want to confuse you guys more. I will do that at the end. Let's do. Let's do this one right here. 56. Good problem. Predict the product of the following reaction. What is D? What does that mean? Does anyone know? So earlier, right? I give you guys this reagent. What's the difference between these two? Sir, what's the difference? Does anyone know? Cool. Yeah, exactly. So it's a very common trick between Orgo II professors. They'll use deuterium to trick you and like kind of blank you, but it's just hydrogen. That's all it is. Just a different form, like an isotope of it. So how does this work? What's the product, right? So we know it's gonna be like a nucleophile because this is like a negative, like this part of it, right? So is it gonna attack the blue or the yellow? What's gonna happen? Yes, correct. So look like this, the final answer. I chose this because I know it's a common trick they do, so don't let that fool you. There we go. Let me think. Then the method goes here. The O goes here. Anti-addition. Or anti-spot. Okay, let me kind of like redraw the D right here. That's the final answer. So yeah, it's a very easy problem, but that's all. All right, that's a good
I have a
problem.
question.
Yep.
So the point of the water is just to protonate that oxygen. So if it didn't have that water, it would just be O minus there.
Correct.
Okay.
Exactly. Yeah.
Isn't there like supposed to be some type of inversion?
What you mean?
Like, didn't we hit a chiral center? So shouldn't like the H and the methyl be like inverted?
What are you talking about? Let me see. Hold on. Before I give you the right answer, I want to give you the right answer. Yeah, you see, look, the methyl, right? They switch positions. So this is different though, because it has like anti-addition. I don't know if you remember, like these are like exceptions to the inversion rule. Like the way you move them is different. So this ME right here, originally it was here, now it's up here. And the D took over the anti position with the OH. So it was in a way inverted, but I wouldn't stress it, to be honest, about that. The most important thing is that I want to kind of like pinpoint about this problem is the D4, because they always ask those questions about that. Like they don't use hydrogen and try to confuse you. Their inversion is like, if it's noticeable, then yeah, but here it's understandable because there's a lot of inversion here. So don't worry about that much. All right. Worry about getting what I just said. Let's see what other pounds you got. Well, this is a tough one. I don't know what I want to go with this one. Should I? You guys want to try 64? You got time? I don't know if you guys are drained already. Did a lot of problems. All right, let's just do it. Mad confusing. Yeah, no. My advice is the textbook. It's your best friend. Where is it? Okay. That's gibberish in the beginning. Whatever. Sachs word. It's asking the question. Okay. Just saying, starting with, forget about all the words or whatever. It says starting with this 3-bromo 1-propyne. Hopefully you guys remember this naming. So because it's important to know that a little bit at least. Right? Well, let's try that better. BR. So it says that we incorporated carbon 7 through 9. So yeah, it labels here 5 and 6 for us. So in this case, this is 7, this is 8, and this is 9. So it's a hard problem. Okay, right? Until there, we're good. I'm also trying this problem with you guys too. I just thought it looked good. All right. The next step, right? We need to find a way to make these work. We need to make this. It's the final. But how, right? We need to attack one somehow. This we need to attack. That epoxide is gonna break. So we need to attack. Attack. How do we attack? Let's go to inner nodes, right? I mean, I'm not going to mine, but you know what I'm saying. Attack or whatever. We need to attack. Therefore, what do we attack with? Nucleophile. We have a BR right there. Boom. What rings a bell? MGBR. We went over this, right? MGBR, Grignard reagent, really good nucleophile. Now I need to decide where it's attacking. Couldn't speak for a second. All right, either in 5 or 6, because it's a nucleophile. It's an attack on 6 because there's nothing attached to it. So attack on 6. Yeah, I mean, it'll work because attack on 6, then I add 7, 8, 9. I need to show how I made that, how I made this a Grignard. So BR. Okay. Damn. How to make this a Grignard? Easy. MG. And over H3 plus to work it up. If anyone's confused, I get it, but it's one of the assigned problems. So now we have a Grignard. We showed that. So now that's what we had. We found the answer basically, right? We have to do a Grignard. So now we need to put it here. So we erase all this. It's asking basically this. I just copy what I put here. The Grignard reagent. But just more, obviously more formal. and then always over H3O plus. So in essence, there was only one step we had to do. Figure out that it was a Grignard that we needed. It wasn't that hard of a problem after all. But did it make sense for you guys? It made sense for me, but I already did this course. So any questions, let me know before I move on from this problem. It's kind of tricky, but
We're supposed to use H3O plus and not H2O.
now you could use H2O, or you could use dimethyl ether like this. That's just like, that's secondary. It's not really, like if you use Grignard, that's important. That's just like how to like protonate the alcohol back. So basically like you could use this as well. You could use H2O. There's another way you could use. You could use this dimethyl ether, diethyl ether, or you could use H2O, H3 plus. Any of these three, you could use as the second step of a Grignard. Okay, if that makes sense. Whoever spoke. So you could put that down anywhere. H3O plus H2O in that. That Grignard, MGBR. It has to do with like Orgo lab. If you took Orgo lab, you know, these could be like interchangeable. Okay. Any questions besides that about this question? No? Yes. All right, I guess not. All right, we got 30 more minutes. Anyone's free to go. I guess I'm gonna continue going. What else? All right, let's do this. We haven't done this. These two. These are exam questions, by the way. This one right here. This one. Just look at it for a second, then I go over it. Well, actually, no. I'm gonna do the mechanism. I don't have time for it. Forget about that question. I'm gonna do this one. So there's always going to be a mechanism in the exam, at least one. So it's fair game from anything. It could be from chapter 13, 16, or whatever he does. So this was in 2019, and we'll do it right now. So it says, make sure you have all the flow of the electrons displayed. How can we approach this? So we had this, the first step you want to do always is look at what changed. What changed? Here we had a Cl, here an ethyl. Well, clearly the Cl is a good leaving group. Keep that in mind. So leaving group left. Break down what happens first before you start your mechanisms. That's your first step you want to do. All right, what you noticed? What else happened? You added two ethyl groups, right? Okay. It's a good note. Next, your epoxide broke. So clearly it's gonna be like, you know, a nucleophile attack to open that epoxide up somehow. So now that we have that down, let's actually start it. Okay, let's open it up. And remember, because this is a negative, we have a negative, positive signs can't be here, can't. All right. All right, so where are we attacking? Red or blue? Can someone answer? Red or blue?
Blue.
Yeah, good. So, all right. Remember, this guy has a negative sign in Grignard's always. So, boom, show the electron flow. That's what we're doing. Let's follow how that looks. So to not confuse you guys. And because we attacked that wedge, that becomes a dash. So whoever acts that inversion, there you go. Because here we only had a wedge. For example, we had a wedge and a dash and we attacked it. What can we change if they already have both of them? And the other one, there was already there, 2, 1 dash, 1 wedge. All right. Now what? What's the next step? So we have an MG just floating around. That doesn't really matter, but just to help you guys visualize everything that's happening. That after went there, right? And we have an MG floating around somewhere here. Does it really matter? Okay. So this is crucial, right? We have an O minus there. We know that, remember the intramolecular Williamson synthesis? Intramolecular. Remember that? Whatever, I'm not gonna write all that down 'cause it's too much, but yeah, that's gonna happen here. We're gonna attack that carbon, and CO is an excellent leaving group, so it's gonna leave. That's what happens. So now what, right? Make sure you copy everything correctly. You don't want to lose points from that. And once again, okay, now we need to think, right? What could be the next step? Remember when it says excess, that means that there's a lot of that. So, okay, we could use that again. like we did up here, we're gonna do down here. Mg Br. For clarity, let's use another color, I guess. Okay. This minus. Okay. It's gonna come. Boom. Boom. There we go. And we're almost in the finish line. Okay. Because we attacked a wedge, a dash. We attacked the wedge, becomes a dash. There we go. But we still have that minus sign. It cannot stay like that, right? Because there's an OH. So we use this guy, the last step. H O O. We could use this because it's a weak acid. So that's why we could use this. The only exceptions. No strong acids. Therefore, we go this, we go right here. Take the hydrogen. And then it looks just like that. All right, that was the mechanism. Any questions? Yes, no? All right, let's see. So I pretty much did every single problem I can to cover everything. Yeah. Yeah, guys. Okay, I'll do one more. One more. Let me try to find it. Where is it? Where is it? Where is it? All right. All right. So it's saying right here, explain the difference in rate between the two reactions. Yeah, conformations. It's asking to just draw chair conformations, basically. Once again, this problem. See, they kind of like flipped in a way. So you do like a ring flip as well. So here, the O is here, the OH is here. All right, terbutyl. Remember when you do like a ring flip, what happens? Just move one to the right, downwards, that's it. All right. I just saw the other ones, I guess, to kind of help show what's going on. Okay. So here we have both on axial, right? Both axial. Like the main ones we care about, the OH and the BR. And this is they're both equatorial. Therefore, more stable. We're just saying, explain the difference in rates. More stable, slower rate. And your proof is the chain conformation, so slower rate. And here, faster rate due to the instability. It's not stable enough. The big groups are not in the right areas or the most stable areas. Okay. I'm ending here. It's 1:47. We did a bunch of problems from chapter 13. There's nothing new he could jump in there and test you on. Everything I did here should be fine. And yeah, so I'm done for today. Hope you guys liked
Wait,
it.
I have a question about this one.
Go ahead.
Like the axial and equatorial. So in this question, we only care about the oxygen, the OH and the tributyl.
Yeah, I mean, the terbutyl, no, we care about the OH and the BR, right? Because that's like the NOH is going to react with them too. See, up here, it's asking about the NaOH. It's saying that it's going to do a reaction with the NaOH. So therefore, the terbutyl is not really coming into play.
But then how are both axial in like the second part? I thought it was when it was pointed to the side that it was axial.
Yeah, it was. It is
Equatorial.
that. It's just that I didn't draw it correctly there. Good point out. I just see it right now. See it? Oh, no. I'll show you right now why. It is axial. I mean, it's equatorial. I'll show you right now. It's supposed to look like this. There we go. BR, and then it goes straight up. Does that make sense?
Yeah.
Okay, yeah. I didn't notice that I drew it straight. Yeah, they're both equatorial there. The turbidor is also equatorial in both sides, so they kind of cancel out. All right, guys. So yeah, that's it for today. I'm gonna find a way to like post a recording somewhere in the drive. But yeah, I'm done and have a good day, guys. Or a good weekend. See ya.
Thanks.
No problem. Any last questions? Go ahead though. All right. There it is.
I have a quick question.
Yeah, go ahead.
So when you studied, you just kind of stuck to the questions that he recommended it to do.
The way I studied last semester was I just did the problems that were in the exams and just all the problem sets. That's it.
Okay, thank you.
That's all you need. And obviously like recitation, obviously if you can come, if you can't, it's okay. But yeah, the textbook is your best friend for this class. And you'll be fine.
Okay, thanks.
All right. You have a question, Sarah? Okay, I guess not. How do I add this?